Hello and welcome to this video where we will talk about the binomial distribution, and we will compare it to the former one that we described, the hypergeometric one. So the binomial law implies something that looks like hypergeometric law, but let's see exactly the conditions that lead to a binomial distribution, and then we will compare them to a hypergeometric. So let's think of a wheel divided into 26 sectors. 6 are white and 20 are red. Our random experiment consists in rolling the wheel 8 times and then note the number of wild results. So it's the fact that you have a few chances to get a white sector each time you roll the wheel. Okay, so there is a probability each time of 6 over 26. So the number of white results after 8 times won't be very big. It could be 1, 2, or 3 maybe white sectors at a total. So the wheel can stop more than once on the same sector. If you viewed my former video on hypergeometric distribution, the example that has been taken was to take 8 letters from the alphabet, and it was to take 8 different letters. So you can't read the same letter after 2 draws. But here, the same sector can be reached twice, for example, or 3 times or 4 times. It's a possibility. The comparison is that if you take a letter, if you pick up a letter in the alphabet at random, once it's chosen, it can't be chosen again. Okay, so that's the big difference here. So the repetition of an element of the initial set of the object is possible. Hence, no combination here. So let's now have a closer look at the 3 points that are important to create a binomial distribution or to discover it. The wheel is divided into 2 subsets. Each time we roll it, the result is a success or a failure. That means here it's a white sector or a red each time you roll the wheel. Second point, the wheel being rolled 8 times, each time the probability of success is invariable. That was not the case in a hypergeometric distribution. Here, each time you roll the wheel, your probability of success is 6 over 26. At the end of the 8 trials, the random variable x is the total number of successes. So your variable has to count the number of successes and nothing else. In that conditions, you can talk about a binomial distribution for the variable x, for the number of successes. And this binomial distribution appears 2 parameters. The first one is the number of trials, 8, that is denoted by the letter n, and second parameter, 6 over 26, the probability of success, p, that is always the same. In this extent, the expected value corresponds to a very simple formula, that is n times p, 8 times 6 over 26, the result being 1.846 approximately. And the comment that we can do on the expected value will be the same as in a hypergeometric distribution. In fact, this is the average number of white sector that you can expect after 8 times rolling the wheel. 1.8 approximately white sectors on average every 8 times roll the wheel. It tells you again that the most likely is to reach 2 successes after 8 attempts. So if you roll the wheel 8 times, the better probability is to reach 2 successes, so to have 2 white sectors and 6 red sectors in the end. There is also a formula for the standard deviation. The standard deviation corresponds to the formula square root of n times p times q. So let's talk about q that I didn't talk about. The probability q is the probability of failure. So it's the complement of the probability p of success. Q equals 20 over 26. Okay? And then when you perform this calculation, your result will be approximately 1.192. So close to 1.2, okay, success. So it's a standard deviation. So again, an average variation of the number of white sectors after 8 attempts, considering that you are trying a lot of times to roll 8 times your wheel. So what it does tell us is that you have got good chances, a little bit more than 2 over 3 chances, to have a number of white sectors being between 2 or 1.8 minus 1.2, if we round the values, and 1.8 plus 1.2. So that gives you an interval that is 0.6 and 3. So every possible result between 0.6 and 3 is a result that is likely, okay, and much more likely than other results. Like, for example, having 0 white sectors or 4 or 5 white sectors after having rolled 8 times your wheel. So we will see that again when trying to get the list of probabilities of each number, each possible number of success. So of course we will graph the results and see them graphically to have a possibility to view them. So you can use your calculator on statistics mode, for example, by using list formulas. And then in list 1, you must put every number of success you could reach. So in 8 attempts, you could have between 0 and 8 white sectors in the end. And you have to appeal to the binomial tool of your calculator. So your formula will look like that. You have to get on your calculator the binomial FDP on a Texas or binomial PD on a Casio tool if you want to calculate every single probability. So how could you reach it? On a Texas, you have to activate distributions thanks to the key's second var. Second var leads to distributions, and then in the list that appears on the screen, you will have to select binom FDP. FDP mentions to function distribution punctual. So it's a French initials. In fact, fonction de distribution ponctuelle (FDP). So it could be FPD in other Texas, and it's PD on Casios. Okay, punctual distributions that allows you to calculate the probabilities of x equals a given number. This given number is a number that has been chosen here in list 1. So that's why you have to tell your calculator to take list 1, the values entered in list 1. And of course, you have to mention the 2 parameters of the binomial law for the calculator. In order, it has to calculate something right. So the results will be these ones. And you can see that indeed, the highest probability is the probability to get 2 successes. Our expected value was 1.8 approximately. So we could deduce that the number of successes that was the likeliest was 2. But one success is likely 2. Okay, and you can comment this list of values by saying that the more you are far from the value 2, and the lower your probabilities will be. Okay, they are decreasing, going to the top or going to the bottom of the list. Graphically, it can be described and visualized this way. So I just put the same values as in the list 2 here. The probabilities to get 6, 7, or 8 successes are very, very low, but the others can be seen approximately on the graph. And you can see that, indeed, the 3 probabilities that are much bigger than the others are the probabilities of 1, 2, or 3 successes. Let's now compare them to the probability that we obtained in the former video on the hypergeometric distribution. So I took the same numerical example with 8 attempts, 6 success elements in the initial population, and 26 elements at the total in the initial population. The only difference between both laws is that the hypergeometric distribution tells us to take 8 examples in the initial set, but without repetition, without possible repetition. Binomial distribution let us take 8 elements in the initial set with a possibility of repetition. And what is the effect, the consequence on the values of probabilities? So let's talk back or get back the values of the probabilities in the former video. This is the fact that the probabilities that are the lowest are in fact higher in the binomial distribution and lower for the biggest probabilities. So graphically, it would look like that. A binomial distribution leads to extreme events are a little bit more likely than in a hypergeometric distribution. And the central events are a bit less likely than in a hypergeometric distribution. Now, let's consider a tree. Of course, the binomial law is associated with a Bernoulli scheme. This Bernoulli scheme begins like that. This is a single Bernoulli scheme that tells you that you've got the probability to have a white sector. So I put a B, sorry, it was for black, but now it's white. I choose white with the probability P that equals 6 over 26. So that's not important, okay? It doesn't matter if it's B or W. However, the second time you spin the wheel, okay, your probabilities will be exactly the same as in the beginning. Probability of success or of failure, okay, and wherever you are in the tree. If you roll your wheel a third time, the probabilities will always be the same again. So let's stop it to 3 trials so as to obtain a tree that can be read, okay? Because if I had to put 8 attempts, I would have 256 bars in the end of the tree, so it wouldn't be easy to read. So let's stop at this point and let's describe what happens in every path of the tree. The number of successes B here, is 3 with the first path, or 2 with the second path, BBR, contains 2 successes, BRB contains 2 successes, BRR 1 success, RBB 2 successes, and so on. We are able, on the right of the tree, to calculate the probabilities to go on a path from the beginning to the end by multiplying the probability that we encountered here on each bar. So for the first one, for example, it's P times P times P. The probability is to have B and B and B. On the second row, we'll be able to write P times Q. So P squared times Q, and so on. So let's display these probabilities for the set of 8 paths of the tree. And we can notice that if we want to reach 2 successes, for example, the calculation of the product of probabilities is always the same, P squared times Q. Okay, they are not multiplied in the same order, but in the end, this is the same result. And here we've got Q times P, P squared times Q. So we can forecast that there will be a simple general formula to calculate the probability of any number of success. Okay, the probability of x equals 3 is p squared, p cubed, sorry. The probability of x equals 2 is p squared times q 3 times, so multiply by 3. 3 times p squared times q. The probability of x equals 1 will be 3 times p times q squared, and the probability of x equals 0 will be q cubed. So this general formula for a probability of k successes, whatever this number, no 1, 2, or 3, or more, considering another tree, has to take into account the number of paths in the tree that lead to the same number of successes. And this number of paths equals the number of ways to choose this number of success among the number of trials. Okay, so what is the number of possibilities to place 2p among 3 places? It's 3 because PPQ or PQP or QPP. And in general, the number of ways to choose k locations among n places is the number of combinations C and K. So for example, here for 2 successes with a tree that contains 3 levels, you've got to calculate C 3, 2. That is 3 in the end. So I will make a video especially for combination numbers and the way to calculate them simply without a calculator. Okay, it will be helpful for those who want to continue after their second year of studies. So now let's just admit this result and then admit that a probability of k successes in general will be obtained by C and K times p to the power of k times q power n minus k. So the probability of success to the power of the number of successes and the probability of failures to the number of failures. That is, for example, p squared times q. That means we want 2 successes and 1 failure. So now if we want to compare this result to the hypergeometric result, why not a tree for a hypergeometric distribution? So the fact is that, and let's go back before, in a hypergeometric distribution, you are not allowing repetition. That means that your probability of success afterwards depends on what have been got earlier. So it's always not the same wherever in the tree. So it's very difficult to build a tree, but let's have a look at it would look like. In this hypergeometric distribution, for a vowel or consonant, taking 8 letters in the alphabet, you've got at the beginning 6 chances over 26 to pick a vowel and 20 over 26 to pick a consonant. But for the second take of a letter, or the second draw, you could say, if you got a vowel at first, you only have 5 chances over 25 to get a second vowel, and 20 over 25 to get a consonant. But if you took a consonant at first, you've got 6 chances over 25 to take a vowel and 19 over 25 to take another consonant. And this continues by the evolution, or with the evolution of probabilities of success and failure, every single case being or having to be studied. So it's very difficult to build a tree in a hypergeometric distribution, so where you forbid repetition. So we still can try to forecast a general formula to have a certain number of success. The number of success is again 3, 2, 2, 1, 2, 1, 1, 0, like in the former example. And the probability that can be calculated are not very simple. But if you are targeting 2 successes, for example, you can see that you will have to multiply for this path 6, 5, and 20 with below 26, 25, 24. 6, 5, 20. For the second path, VCV, you have 6, 25. So you will still have to multiply the same numbers, 6, 25, instead of 6, 5, 20. And if you target this value 2, the numbers to multiply will be 20, 6, 5, always the same. So it's possible to try to get a probability going like that, okay, through a tree. In fact, the probability of x equals 2 is 3 times, because there are 3 paths on the tree that leads to 2 successes. So again, our combination number C32, like in a binomial distribution, multiplied by on top 6 times 5 times 3, and at the bottom 26, 25, 24. And knowing that, you can try to create a general formula, whatever the number of levels in the tree, and whatever the probability of success at the beginning. Why not? But it's not simple, okay? And I won't describe it in details, but here is the general formula that corresponds to what we wrote for our single example on the top, here at the top. 6, 5, okay, is the representation of this fraction. 20 is, in fact, the representation of this fraction, so it's not very simple. And 26, 25, 24 is the representation of this fraction below. And this can be simplified, okay, as a general calculation simplification like that, and you will be able to recognize the general formula of a probability in a hypergeometric distribution with the 3 combination numbers. So it's not obvious for you, I guess, and it's not necessary to be able to do that. Okay, so that's good news. It's not necessary at all. But if you've got questions about that, please ask questions in the commentaries of this video. don't hesitate to comment. So that was just the reason why we don't create a tree for a hypergeometric distribution in general, because it's complicated. So we just have to trust the general formula and to apply it directly. So a last item here before going to exercises in the next video. Is it possible to use a binomial law to describe a hypergeometric distribution? So instead of a hypergeometric distribution, we would like to use a binomial one. So first, why would we do that? The problem, and let's go back, the problem with the formula of hypergeometric distribution is that it contains 3 combination numbers. And this is a problem. This was a problem 2 or 3 centuries ago, of course, but it's still a problem today for our computers or calculators. If n, so the little n of the n in capitals, begin to be big, so if we talk about big populations and big samples in the population, the combination numbers will exceed the capacities of your computers or calculators. So if you take a value of a size of population of, for example, 1,500 and a size of the sample of 500, your calculator is unable to calculate you this number of combination. See 1,500, 500. Now it exceeds the memory capacities of your calculator. So it's a problem. And this problem doesn't appear in the formulas of binomial distributions. So it would be still good news if we were allowed to use the formulas of a binomial distribution instead of the formulas of an hypergeometric distribution. So if we're going backwards here, we would be able to compare the formulas of the expectation and of the standard deviation in both laws. In a hypergeometric distribution, the expectation is calculated thanks to n times a divided by n capitals. In a binomial distribution, the expectation equals n times p. But a divided by n capitals equals p if you consider the first level of the tree. 6/26 is exactly the probability that we got in the binomial distribution just earlier. And 20/26 as well for the failure probability. So if you could consider that even in a hypergeometric distribution, your probability of success doesn't evaluate a lot, and it could be the case if the numbers at the beginning would consist in or would correspond to some criterion, maybe the binomial distribution could lead to good results or good enough compared to the right results thanks to the hypergeometric. So it's a fact that it would be useful, really useful, to use a binomial distribution instead of a hypergeometric one, taking the parameters of the hypergeometric distribution to obtain the parameters of the right binomial distribution. So let's have a look at what give us the two laws, binomial or hypergeometric, in terms of probabilities of successes. So you've got here a certain number of successes with certain parameters. So you've got a population of 30 elements. Inside them, there are 6 success elements. So it's 1/5 as a proportion in the population. And you have to take 5 elements at random in this population. This way, with the binomial law, you allow repetition. and the probability of such number of successes are these ones. With the hypergeometric distribution, you forbid repetition, and then the conditions of the draws are not exactly the same, so you can see differences in probabilities of such number of successes. So these differences are quite big, okay? They are very, very visible. It's approximately 10% for the two first. It's approximately 5% then. It could be 20% here, and so on. So that's big mistakes created by a binomial distribution if you consider that the case, the real case, is hypergeometric. So a binomial distribution couldn't be used to talk about hypergeometric results. Okay, it won't be right as a result if we took this kind of parameters. But if we change parameters, let's choose, for example, 5, 30, and 200, we can see that both laws give results as probabilities that really look like each other. So obviously the differences can be seen still, but the differences are much lower than in the former example. And so we can see that if, for example, n in capital begins to be big, maybe binomial or hypergeometric lead to the same kind of results. So why would it be the case? Because if you are taking elements inside a big population, forbidding or allowing repetition will lead to approximately the same kind of situations because your chance of repetition begin to be low. So if you forbid it or if you allow it, won't make the difference. Okay? So the criterion that has been adopted here is that if the size of the population is more than 20 times the size of the sample, so it's true here and it's wrong here, you can use a binomial law instead of a hypergeometric one, even if the repetition is forbidden. So our criterion will be this criterion. So, it occurs in a lot of examples, okay? If your population is very big compared to the size of the sample, you can use, in any case, a binomial distribution, considering that your probability of success will be approximately always the same. So, it appears a lot, and the most interesting case for us is the survey. If you are performing a survey by interviewing people at random in the street, you are interviewing maybe 100 or 200 people. So it's a big number for n. But the size of the population is almost in any case much bigger. Okay, for instance, in a city that has 3,000 or 30,000 inhabitants, taking 100 or 200 people to interview is very little compared to the size of the population. And to interpret, analyze, comment the result of your survey, no software will use a hypergeometric distribution because it will be unable to use the formulas of the hypergeometric distribution. But we know that we are allowed to use a binomial distribution, and then a computer would be able to calculate things and probabilities with a binomial distribution formula. Okay, let's stop here for the presentation of some elements, criterions, characteristic of the binomial law and the comparison between both. Next time we will talk about the Poisson Poisson distribution. Let's pronounce it in French because he was a Frenchman. Poisson distribution. Okay, and we will see why a Poisson distribution is sometimes used instead of a binomial distribution. And we will see again and again that distributions can be used instead of some others if some kind of criterions are met. This is a general rule in statistics and in inferential statistics. Okay, bye and see you in the next video.